Hello everyone. This lecture will be concerning the full longitudinal motion dynamics and how we can design the stability augmentation system using the Bhaskara method. In the Bhaskara method, we have briefed in the last lecture. We can find the control matrix K equal to P W transpose whole inverse alpha minus A. So here P is the, let me write, the P is the contributing test matrix, W triangular matrix, which will be formed using the polynomial of the A matrix, system matrix, and alpha equal to coefficients of Bézier closed loop poles and A coefficients of open loop poles. And the problem is, the example we are going to solve is how we can design the stability augmentation system for the longitudinal model of aircraft. Problem. Consider the longitudinal model of an aircraft. Here we have the derivative part of the state vector, del u dot, del w dot, del q dot, and del theta dot. And the stability derivatives, which forms the A matrix, minus 0.01, 0.1, 0, and minus 32.2, minus 0.4, minus 0.8, 180, 0, 0, minus 0.003, minus 0.5, 0, 0, 0, 1, 0. And we have the state vector del u, del w, del q, and del theta. And we have the control matrix B, 0, minus 10, minus 2.8, 0, and we are assuming only the elevated deflection as the control input for this system. Now, to design stability augmentation system using Bhaskara, this is a numerical method, Bhaskara method, such that augmented aircraft, augmented means the closed loop system, has following short and long period characteristic as for short period the damping ratio 0.6 and natural frequency short period 3 radian per second. And for long period, the damping ratio P for phugoid, also long period motion or sometimes called phugoid motion, 0.05, and natural frequency for phugoid motion, 0.1 radian per second. It is clear from this given value that damping ratio for the long period is quite less compared to the short period motion. That's why it takes more time to get stabilized. Now we'll be using this Bhaskara method to solve this problem. This Bhaskara method, how to find the control matrix K. Here we'll go step by step. So first we'll find the open loop characteristic equation. So we can find the system characteristic equation, the SIST solution, the system characteristic equation we can find Si minus A equal to 0, and here since it is fourth order system, we'll have S into the identity matrix, which is 4 plus 4, 0, 0, 0, 0, S, 0, 0, 0, 0, S, 0, 0, 0, 0, S, minus the system matrix minus 0.01, 0.1, 0, minus 32.2, minus 0.4, minus 0.8, 180, 0, and 0, minus 0.0, 0, 3, minus 0.5, 0, 0, 0, 1, 0, equal to 0. One thing I should say, this data, what you are considering in, so you can use the poly P, and if you enter this, you can get the equal to 1, 1.31, 0.99, 0.029, and 0.038. And if you use this coefficient of the polynomial, the polynomial equation you get is to the 4 plus 1.31 s cube plus 0.99 s squared, 0.029 s plus 0.038 equal to 0. Or if we write in A's form, that is, we can write s to the 4 plus a1 s cube plus a2 s squared plus a3 s plus a4 equal to 0. And from this we can form the A vector, which is a1, a2, a3, a4. And from these values we can write 1.31, 0.99, 0.029, 0.038. Right. And also we can find the open loop holes, we can use the damp parameter, or you can use R equal to roots of P. And from this, we can find S12 equal to minus 0.6 plus minus 0.7i S24 0.01 plus minus 195. Okay, this is quite obvious from this poles, this part. It is basically short period and this is basically long period motion, right? So these are the poles of the original system A matrix. Now we'll form the de Sitter characteristic equation. De Sitter correct. Okay, one thing if you notice here carefully, if you notice here the poles of the original system, one positive. So this actually you can see the system handling qualities is 4. You can say for this pole the aircraft has 4 handling qualities. So we have to design a control system which can improve these 4 handling qualities. The de Sitter characteristic equation we can form. We can find s squared plus 2 zeta short period omega n short period omega n squared short period and s squared plus 2 zeta p phugoid omega n p phugoid plus omega n p squared equal to 0. And these values are given to us. If you go back to the problem, these values are given. Right. So if you substitute these values, we can find the de Sitter characteristic equation that control system should follow. So substituting the values of zeta and omega n in this equation, we have s to the 4, or we can write s squared plus 3.6s plus 9 into s squared plus 0.01 s plus 0.01 equal to 0. And if you multiply both the polynomial, we'll have s to the 4 plus 3.61 s cube plus 9.05 s squared plus 0.126 s plus 0.09 equal to 0. Or we can write in the coefficient, we can denote as alphas. If you write s to the 4 plus alpha 1 s cube plus alpha 2 s squared plus alpha s plus alpha, so it is 2, 3 and 4 equal to 0. Or we can write alpha 1, alpha 2, alpha 3, alpha 4 equal to 3.61, 9.05, 0.126, 0.09. So we have formed the A and alpha here, which is going to, so we have found this and this. So now we have to find P and W. So once you find that, then we can use the main equation to find the control matrix K. So now we have to find the P matrix or contribute test matrix. So we can write contributing test matrix. We can write P equal to B AB A squared B and A cube B. And if you also use then the MATLAB command P equal to CTRB contributive matrix A comma B, and if you enter it, we have P matrix as 0, -1, 40.57, 19, -10, 4, 496, 6, 5, 4.6, -400 in 0.76, -2.8, 1.43, 0.77, -2.35, 0, -2.8, 1.43, 0.77. This is the contributed test matrix. So P has been found. Now we have to find the W. So W can be formed. W. We can use the terms A is what we have found before, the polynomial of A matrix, 1, A1, A2, A3, 0, 1, A1, A2, 0, 0, 0, sorry, it will be 1, A1, 0, 0, 0, 1. And if you substitute the parameters what we had before, this A here, so this parameter if you substitute here in this matrix, we have 1, 1.31, 0.99, 0.029, 0, 1, 1.31, 0.99, 0, 0, 1, 1.31, then we have 0, 0, 0, 1. So we have found the double matrix. Now, another important term in the Bhaskara method, if you notice this term, to find this term also very tedious. So let's calculate this. So now we'll find, if you use MATLAB easily you can find, or if you in the MATLAB you can easily put what for this parameter PW transpose and inverse, but we are directly writing here the value is found to be, you can request it to use the MATLAB code to find this matrix. So value is obtained to be 0.008 minus 0.001, 0.0004, and 0.013. 0.001 minus 0.001, 0.002 minus 0.001, minus 0.36, 0.0068, and minus 0.008, 0.005, 0.032, minus 0.13, 0.44, and 0.24. This is the term PW transpose whole inverse. Now we can use all these values in the control K equal to control matrix PW transpose inverse alpha minus A. So we have So this matrix already have found. So here we can write. So here we can write this matrix again. 0.0008, 0.001, 0.004, 0.013, and 0.001 minus 0.001, 0.002 minus 0.001 minus 0.36 minus plus 0.0068 minus 0.008, 0.005 minus 0.013 and 0.24, and into we have alpha minus a, so alpha 3.61, 9.05, 0.146, 09 minus, right, minus 1.31, 99, 0.029, 03. So the final value yields to be minus 0.005 minus 0.012, 0.770, 0.065. So this is basically our control gain vector, and the control del E we can form as KTX, or we can write K transpose will be, this will convert to row vector, so minus 0.005 minus 0.012 and minus 0.770 and 0.065 and into del U, yeah, del W, del Q and del theta, and the control algorithm found to be 0.005 del U plus 0.012 del W plus 0.770 del Q plus 0.065 del theta. Right. So here we can, if you draw the closed loop block diagram to show how the control system can be designed for this particular system. So here we have the dgr value, x dgr. We have, for this particular case, we have 0, 0, 0, 0 to maintain, and we have the control where we are designing the K, and from this K we can form the control which is minus K transpose X. So here, if you notice here, we are having minus K here, which is E equal to error, and this is going to the plant x dot equal to AX plus BU, and we have the output which is X is nothing but or these states del U, del W, del Q, and del theta. And we have the feedback here. This is negative, this is positive. So this is the basically control system for this particular motion dynamics, and we can control all the state in the system. Now, the question is, how, if you notice here carefully in the example, or the examples we have taken so far in this course, we are assuming one control input, right? So this is actually making our, maybe the problems is easy to design the control. But what will happen if the system has x dot equal to ax plus bu, and for example u is not a scalar. If it is vector, what will happen? So in the next lecture we will be taking the lateral stability augmentation, and where we will be using two controls. So as of now we have discussed, last two lectures we have discussed how we can design the longitudinal stability augmentation. In the next lecture, we'll be discussing the lateral stability augmentation, where we'll be taking more critical system where two control inputs will be there. And having two control inputs, there's some different terminology you have to use to design the control. And the MATLAB code for this example, this is the MATLAB result we have. So we have found this A here. This is the B basically here, and the closed loop control system. And the rest of the code you can easily write how to find the response of the individual state. So that is common for all the system. The way we did previous example, how to find the response, you can do it. So we have to find the closed loop system model, and you can you have to use the initial command initial, which will give you the state information, and you can plot over time. So let's stop it here. We'll come up the new topic in the next lecture, lateral stability augmentation, how we can implement for the multi-input systems. Thank you.